the way the course is structured is it's going to be mostly a lecture style, and we have slides that show code and then I'll explain the code. And that's purely because we don't have time to go over everything where I interactively go through all of the code. That said, there is time if something doesn't make sense for me to go over the code interactively for a section. Okay, so if anything doesn't make sense and you need me to go over it in more detail, that's very much just let me know and we can do that. Okay, and so it's up to you guys what sections we do that for. Let me see if there's anything else I need to tell you about. So to try and help also with the interactivity help me get a gauge of what you guys are understanding and not understanding. We're going to try out using polls for the first time. And so they're going to look something like this. We're going to do a trial run right now. And so this will just be a poll about everyone's coding history. And so I'll give you 30 seconds to fill it out. And so these are not just useful for us to understand what you guys are good at, what you understand so far, but this also helps us gauge who's actually here, who's paying attention, and so we can get to grips with how the course is going in general. So it would be really useful if you stay with us and participate as much as you can. Okay, so we'll just end the poll there. So it seems that a lot of you do have experience in R, over half of you, which is cool. And so, oh yeah, so someone mentioned Perl. I forgot to add Perl in the list. Sorry, that should be on the list because a lot of people do still use Perl. But it seems like we have a good spread of people that have some experience in something, and then we have a good chunk of people that have no experience. I can share the results. There you go. That's what it looks like. And so that's what you guys, the demographic coming into this. So it is quite varied. Cool. But what we're hoping is that with courses like this, we can bring everyone up to the same level. Okay. Cool. And so I'm going to start sharing my screen. And I'll show you where all our material is and how we are structured. Okay, so hopefully a lot of you would have found this when you started setting up your course setting up your computer with the requirements we have. Okay, so if you give me 2 ticks, I'm just going to rearrange my screen so I can see the chat as well. Where is chat? There we are. Okay, so what we have here is we have our training homepage. And so you can see links to other things we do, like software that we've built and analysis. So you can find out how to work with us for other things. But this is our main hub for where all our training is. And so if we scroll down, this is the table that contains all of the training that we have available. And so over the next few days, what we're aiming to get through is these 3 and the tidyverse as well, which is a separate one. And so what we're actually going to be doing specifically today is this, the intro to R. Okay, and then tomorrow we'll do plotting in R. And then the 3rd day on Wednesday, it's going to be really focused on reproducibility. So this is actually one of the most important skills, I think, but the most important skill that no one does. So I think it would be really important that everyone comes to this one because we're going to be covering how to use GitHub, how to make reports, and tidyverse, which really accelerates your coding. It changes the logic you use when you code from this first day and makes it super streamlined and much more intelligible. So with these 3 days, hopefully you'll have a really good base for everything. Okay, and so if we link through here, we get to the course page. Okay, And so this is the structure. All of our courses have pages like this. And we have these checks. These are really important for us, but also for you to show that we've built the course is building correctly, okay, because we automatically build everything. And then number 2 is working on all systems. So this means everyone, no matter what system you're coming from, whether you're using a Linux machine, an Apple, or a Windows machine, all of the code should still run on your machine, okay? And so most of you would have gone through these system requirements. You've installed R, you've installed RStudio, and got some of the packages you need for today. And so that means we can pretty much dive into the sessions, okay? I guess the other thing to note is at any point if you need help, obviously you can message us in the chat, but if you need help after the sessions, you're reviewing the material, what you can do is you can click on the Getting Help, and this takes you to GitHub. And where it takes you on GitHub is the issues page. And so this is where it's associated with our GitHub repository that has all the teaching material for this session, so Intro to R. And we have, you can see here, some people have brought up issues in the past when they've been going through this course. So someone had an issue installing Rio, for example. And so we can go in here and you can see that we've responded to that with some fixes to help. Okay. And so this is our best way of doing this because it's a public place. So it's easy for you to see. And so if someone else comes in with a problem with Rio, then they can just read what we wrote in the past, and it makes everything a lot easier. So yeah, all you have to do, first you'll have to sign up for an account for GitHub, but we'll be doing that. Everyone needs to really do that by Wednesday as well for the course. And then you just create a new issue. You can write your question in and then submit that new issue. Okay. Oh, yeah, I'm not signed in, so it won't let me do that, but it's pretty self-explanatory. Okay, so that's how you get help after the course. And you can do that for anything. So if you see a typo, you can suggest a fix for us. If something doesn't make sense, if you're having installation issues, or if you have an idea of something useful, like a couple extra slides would be really useful to further explain this, or to add an extra thing. You can think of it as almost a suggestion box and a help place. Okay. So the contents for today, we have our HTML slides here. We also produced all of the content in a single page format as well. Some people prefer that because it's, we can have a quick look. It's like a worksheet. And so you can just work through it slowly like this. And then we have a final one, which is just the R code itself. So you can just download the R code. But we're going to be working from the slides. And we're ready to go. Okay. And yeah, like I said, just give me a shout. Feel free to be as interactive as you want. I do know there's also some construction work going on at my end today. It's pretty quiet, but if that becomes a problem, you just got to let me know and I'll see what I can do about it. Okay. Cool. So introduction to R, session 1. So we'll first go over a little bit of the setup. So hopefully everyone would have downloaded everything that they needed to. They had no issues with setup. I had only a couple emails asking for help with the setup. So that, I'm assuming, means everyone else had no problem at all, and is not furiously doing it right now. But I know that I know that not everyone can do it right away. Everyone's busy. So the way that we have the courses structured is everything is in the download. So if we can see, we have a link to this download here. The link was also on the page previously. And within this download, in the R course, there's a folder called presentations, which means you can look at all these slides locally, okay? And the R code, everything we're doing, you can then use locally. So if you don't have the internet or you're traveling, something like that, you can review this. We also have the exercises and the answers. So there's exercises as we go through, and you'll be able to access those as well by following this directory structure. When you have RStudio open, it will be as simple for all the code to run. You'll just have to run this command set wd, and you put in wherever you downloaded the course. Then you'll be going into intro to R one day, and then you'll be directing yourself to R course. Okay, and so what this means is you're changing the viewpoint of where your RStudio or R is looking. Okay, so it's similar to when you have Finder open and you just, where are you in the Finder? And so using this means you'll have access to all of the materials as we kind of expected and lay them out in the course. And so as there might be at some points you would need to read in a folder or a data table. And so we'll provide the path that you need. All the code will work as long as your working directory, which is, like I said, the viewpoint is set to the correct place. Okay. But if anyone's having any issues with that, we can revisit that in a little bit once we've introduced R in RStudio. Okay, so what is the background of R? So it was created relatively recently, well, 30 years ago or so, I think. And it's a scripting language that's predominantly used for statistics, okay? And so you'll notice that when we did the poll, we had a lot of different answers, Python and C++, things like that, SQL. A lot of these languages are very, very popular and more popular than R generally. But when it comes to statistics, which we do every day as biologists, then there's nothing really that competes quite with R. And so it was developed by these two gentlemen, and they developed R in response to S, essentially, which came from Bell Labs. And really what their strengths are, it's all about this very high level data analysis. So it allows you to do a lot of statistical approaches. It's open source and cross-platform. So you heard me earlier emphasize that all this code will be working on your Windows machine, on your Linux machine, on your Mac. So this really boosts collaborativity if everyone can use it. The graphics capabilities are really strong. Actually, R is one of the best graphing packages or softwares out there. If you need to make plots, the people will often do analysis in other languages and then come back to R, even if they're not super strong with R, just so they can make the R plots. There's lots of packages that can be added on, and there's a big community of developers. And so the community are making packages that are then going to be open source that can be just shared with everyone. And in theory, the documentation is very thorough. And that is a majority of the time is the case, although like with everything, it's best laid plans and all that. And so straight when you download R, you have a lot of the capabilities from the get-go. You can do a lot of your basic statistical analysis. You can do a lot of plotting very easily. And then you can download lots of other packages from places like CRAN and Moran and RForge, which take this to a new level. And so these are packages created by, a lot of the times, people like you and me who needed to do something. They figured out a statistical way to do it. They realized there wasn't a package, and then they wrapped it up and submitted it to CRAN. And so it's scientists, it's data people, it's people working in business, all kinds, supporting the community. And so in particular, Robert Gentleman started something that was really important for us as biologists, which is Bioconductor. And so this is a group of like-minded biologists who are also working with data, and they really focus on making these packages which will help bioinformatics. And so we actually, a couple of years ago, had the Bioconductor conference, and Robert Gentleman come to speak at that at Rockefeller, which was really great. And you got to see all the diversity of packages and what people are making. And so you can see this graph is a little outdated now, but you can see that R is really accelerating as one of the main coding platforms that people are using for sciences because of its strengths. And so hopefully everyone has now downloaded it. You can get it from the R project website. And then what we're going to be using R with is RStudio. And so what RStudio is called an integrated development environment. And so what it does is it takes the command line version of R and makes it much easier to use. And so I think I'll switch screens to show you this. Let me just grab my RStudio up. So this is my RStudio right here. It might look a little bit different to yours because I have different colors, but you can change that. You can see here I set my working directory to be in the right place. And so what you have up here is you basically have these 4 panels which are adjustable depending on what you're doing. And at the top you have your scripts that you're writing. So this is essentially like a text editor. Down here you have your console. And so this is the bit in regular R that you have. So the nice thing about this is you can build your scripts and then submit them directly to the console, see what breaks, edit your scripts again, put them back in the console, things like that. You then also have access to what's in your environment. So my environment is empty at the moment, but you can also see that. You can see your history, what code have I done, and other things like Git, which will be important later on. You can see where your files are. So this is just to navigate around your files, just like Finder or something like that. There's a plot window. So when you build plots, it goes straight to here and you can see them. You can see what packages you have installed and you can get help. So you can see I was looking for help with the string R package, which we'll cover in tidyverse. And so I wanted to make sure I knew what the arguments were for that. And so you can get help with that. And so this is really nice because RStudio just allows you to have a lot more information at your fingertips, and it makes working and coding on a project so much easier than just using R, like vanilla R on the console. So that's why we advocate R. This is what we advocate RStudio as well, because it's going to make your life a lot easier. Okay, so let's get started with getting into what R can give you. And so just as a heads up, I encourage people to code along as they go if that works for them. I find that obviously doing something is a much better way to retain what's going on. And I'll try not to speed through the content too much so you actually get a chance to do that and you don't feel left behind. But if you need me to slow down or speed up at any point, just let me know. Okay, so the big part, one of the big parts of using any coding language is you'll have lots of different data types. Okay, and so the different data types will fill different roles, and understanding what data types are available in your language of choice is really important for you being efficient at coding. And so R has a lot of these common data types. We have things like data frames, matrices, lists, vectors, and variables. And then you can also just do very simple calculations that don't need a variable in them. And we'll go through this. So at its base, you can just use R as a calculator. It's a very fancy calculator, but it is just a calculator. So you can just do things like 3 + 1, and the answer will come back on the console 4. Or you can use the asterisk as the multiplier. So it'll be 2 × 2. And then you can start to do more complex things. So here we have a function. This function is sqrt, which you can probably tell means square root. And so we can start to stick things like these functions together with simple calculations. So here we do the square root. We have the parentheses, and so they're the curved brackets, and we have a number in between. Okay, and so that means we're doing the square root of 25, and then we're subtracting 1, and that's how we get to our answer of 4. And so when you start to use functions, this parentheses, these curved brackets, are what demonstrates that you're using a function. A function has lots of hidden operations underneath the name square root, and so it means it's doing something complex. And this could be thousands of lines of code, or it could be 2 lines of code, what it's doing. But it's all named and hidden behind just this single thing here. And so what goes into the function and goes into the parentheses is the argument. Okay, and you could have 1 argument, you could have 10 arguments, you can have as many arguments as you want. And then once you execute the function, it will resolve the code in the function and then give you your result, just like it would 1 + 1. And so some of the really simple functions, all you have to do is give them a number and they'll give you an output. And so in this case, it's a single argument and it's giving you a number output. Sometimes there's some other kind of these simple functions like min, sum, and max. You can give them multiple arguments and you separate them by a comma. And this time it's going to take these numbers, and then it's going to ask for min, just what's the smallest number. Sum, it's going to add them together, and max, it's going to tell you what the biggest one is. Okay, and so these are some of the simplest functions, because all they're doing is they're taking some numbers, or a single number in square root's case, and it's evaluating them through a very specific lens, so min, sum, or something like that, and then it's giving you an output. Okay. So R has a lot of these functions built in, and so this is what I talked about when R has a lot of functionality out of the box. If you click here, we have a link. Oh, my mouse is being funky. Okay. So this is a very short list of some of the functions, some of the common ones, but you can see some things to do with the distributions, Poisson distributions, some statistics, SD, scale, sequencing, generating sequences, lots and lots. And these are just really the super basic ones that we use kind of commonly. And like I said, you can also load other ones in, and we'll show you how to do that later on in the course. But these really gives you access to the specialized tools that you might really care about. Like for us, it's all about taking a fast queue. We can QC that fast queue. We can then align it, do stuff like that. And you'll need specialized tools to be able to do that, but you can do it all in R. And so when you're in, if we go back to our studio, okay, If you have a function and it's not working for whatever reason, you can just do the question mark. Okay, and so you can see it comes up over here. It tells you the help for this specific function, and it could be for anything, any function you're looking at. And because you're using RStudio as well, you can also do this very interactively. So because we're on the help tab now, I can just search for anything. So if I want to find out about the correlation function, core, okay, and then it tells you things like what arguments go where and what those specific arguments are. And then at the bottom, it often has some examples. Okay. Okay, I think I need to give up on my mouse. Okay, so this is how you find help. Obviously, it's a very specific result that you get back. It tries to answer most of your questions, but a lot of the times you'll have other questions with your function, and that's where searching online is often a good resource at that point. But for some of these very base functions, like square root, you shouldn't have too many issues beyond having to use a question mark. Okay, so as you saw in the help that I did for correlation, there were lots of different arguments. It's a bit more complicated. You can imagine you have to provide what kind of correlation you want to do, as well as the two things you want to correlate. And so the function needs to know which of the arguments is which. And so the name and the order are quite important. And so when you look at things like min, it doesn't really matter. It doesn't really care. It's a very simple function. So we can switch them around. You'll get the same result. But if we look at something like dir, which is for the directory function, we can see it's not the case. Okay, so I'll quickly switch again. So what dir does is it lists the files in a directory folder. Okay, and so the first thing it is expecting is something called the path. So that's, do I need to look in where I am right now, or do I want to look somewhere else to look for files? Is there a pattern? Do you want these only to look at files that end in a certain ending, like .text or .r markdown? Do you want their full names back? So that means their whole path. Do you want to look through recursively? Things like this. And you can see that each of these arguments has a name and a default and an order. So path is first. Okay, so by default, it's going to look, the full stop means it looks where it is right now. Yeah, and that is the first argument it's expecting. So if in this case we want to know the full name, what we need to do is actually specify. Okay, so we can do dir by itself, just dir, or we can do dir full names. So I'll just show this. Okay, so we do dir. That tells you what scripts I have, what files I have. And then we do full names equals true. So we've decided we want the full names for this. And so this provides the full names. Yeah. And so if we remember here, full names is the fourth one. Okay. So if I just put in true, and I'm not specifying which is which, it gets upset. Okay, so I just got a question. Didn't you have to insert the argument of path under dir first? Yes. That's if you want to change it from its default. Okay, so a function will go to its defaults first, but here we actually provide the name. So this is what I'm explaining right now. Here we provide the name. So it knows, actually, it doesn't matter which one it is. I'm going to go to full names, and full names will be true. But here, if I just provide true as its first argument, it gets confused because it's invalid path argument. Okay, so because I'm not told it which argument it is, it's assumed it's the first one. So now if we go back to our slides, you can see that if we enter this in, that is exactly the same as doing this. Okay, it's assuming these defaults are true, and then it's adding in full names equals true into the fourth argument. Okay, so you can see here how the names and the order of a function's arguments are really important. And that's 9 times out of 10 when a function isn't working, it's because you're missing one of the arguments, or you've misspelled one of the names. That's most of the time. Okay. Ooh. So next we're going to get onto something more complicated, and that's variables. I was just checking to see if we had a poll yet. We don't. And so pretty much every programming language will make use of a variable. And basically this just means we're saving something. Okay. And we can save something we're creating in R as anything else as long as it's a character. And so in this case, for R, we have to basically assign this whatever we're creating and using this little arrow. Okay. So this is the less than sign and then a hyphen. And so when we do that, we're now going, we want X to be 10. Okay. And so we're assigning the 10 to the X. Yeah. And so we have a question from Javier. Can you use equals instead of the assignment operator? You can. Okay. So in a lot of other language, what people use is the equal sign. The general consensus within R is that it's bad coding practice because the equals isn't clear about the directionality. It's not as easy to read, but it does mean you have to put in 2 characters instead of 1. So I get, while you're coding, equals may be easier and it may make more sense. But as a general coding practice guideline, most of the time people will encourage you to use the assignment operator, which is this. It also makes things more clear later on when we start to do things with logicals. And so a logical operator will often use double equal signs to say, is X equal to 10? And that's a question. Is X equal to 10? And the only difference there is there's an extra equal sign. And so that is harder to read if you are using both single equal signs and double equal signs in your code. But 100%, if it's easier for you, do it. And if that's what you're used to, it's just a matter of coding practice as opposed to like coding law or like the rules. Okay. So once you've assigned something, so here we're assigning 10 into X. When you just type X into your console now, it'll give you a 10 back. So it means in your environment now, you have X saved and X has a value of 10. And so you can assign anything we create, anything you create as you go. If you create a data frame, you create a matrix, or you just, in this case, entering 10 into the console, you can save that into an argument or into a variable even. And then that variable has that inherent value. And then you can use that variable in other things going forwards. And so when you create a variable, they're very flexible. You can change them. And so in this case, In this case, we have x is equal to 10, and then we use the assignment operator x, we reassign it to 20, and now we'll replace the 10 with 20. Okay, and so now x is no longer has the value of 10. It's no longer a container for 10. It's a container for 20. Okay, so we have a question from Greg. What about going the other direction? Okay, so everything I've shown you from so far is going from right being assigned to left. Does it matter stylistically? Consistency is one of the key things with making clear code. And so stylistically, what people do is they always assign from right to left. You could go left to right if you want. It still works. It won't break, but it makes it harder to read. Yeah, so this is all about, it's not just about collaboration and being able to share your code with people. It's about being able to come back to your code 3 weeks later and understanding what you did. That's most of the time why clear code helps you. Because if you don't do that, you're not like making clear code and it's not commented, so you understand what's going on. It can be really, really hard, especially when you're learning. Okay. So now we have x, it has 20 inside it, and it's saved as 20. You can then use these variables as those values. Okay, so x equals 20, x and 20 are interchangeable. And so we can do x plus the square root of 25. So we know that's 20 plus 5, and we get 25 back. Okay. And then you can keep going and you can create new variables using this exact method. So we can say x plus square root of 25, and we assign that to y, and now y is 25. Okay, so that's variables. Variables are fairly, like, in principle, pretty straightforward. They're saved in your environment, and they're little placeholders that you can assign things to represent. And like I said, pretty much every language has one. So if you're familiar with other languages, then you should be familiar with the concept of variables. Okay. So next we're moving on to vectors. Vectors are where we start to get into interesting data types. Okay. So most of your really basic variables or data types and everything we've looked at so far pretty much is a vector. Okay, and so a vector is it's an ordered collection of values. And so we created x and we created y. They're both vectors and they have one entry in them. And so that means they have a length of 1. And so you can say we have x. We can use the function length on it, and it'll tell us we have a length of 1. Okay. But vectors often have a much longer length. They can have multiple entries. And so what we can do to create these vectors is use the combine function. So that's a C. And so what C is doing is it's taking all of the different arguments that you provide it, and it's sticking them together, and then it creates a long vector out of it. So here we're assigning 1 up to 10, all separated by these commas. We're assigning it to x. And so now when we put x in, you can see that we get 1 through 10 back. Okay. And this isn't just one string. It isn't just one long line going 1, 2, 3, 4 with no gaps. Each of these is a separate entry. And you can tell that because you can do length again. And now it says it's 10. So this means we have 10 entries in this variable x. And this variable x is a vector. And so this is it's a one-dimensional array, essentially. One of the useful functions we can use, or useful shortcuts we can use, is the colon. Quite often we're using vectors of numbers to, as you'll see later on, you can use them to do indexing and things like that. And so Here you can use the shortcut of the colon to say, I want 6 through to 10. And so we can assign that to Y, and you can see 6 through to 10 is now available. There are other operations, other functions that will help you do similar things, but they're more complicated, and these are seek and rep. And so both of these will create these stretches of numeric vectors, but they have a very specific kind of numeric vector they're producing. It isn't just one sequence from like 6 through 10. And so what seek will do is it will, you provide it a start and an end and how many you want it to skip, essentially. So that's a from and a to and a by. And what it will do then is it will create this recurring number. Oh, yeah, we had a question about length. And I think it's just the spelling of length. I think, yeah, Greg took care of that. Thanks. That's good. Helping each other out. Cool. So, oh, sorry, my notifications are on. I should turn those off in a sec. Okay. So, yeah, we're doing seek and rep. So you can see with seek, you can create this numeric vector that's 1, 3, and 5. And we're saying we'll start at 1, we go to 5, and we want to have it every 2 times. So you can see how you can start to make more complicated numeric vectors with this. Then we also have rep. So what rep does is you provide it with a number or a vector, and it will repeat it a given number of times. So here we have a vector we're giving it, 1, 5, and 10. And we want it to repeat it 3 times. So you can see we got 1, 5, and 10, 1, 5, and 10, 1, 5, and 10. Okay, so these are super useful functions. They seem straightforward and they seem like, why would I use this? But later on, you'll see that when we start to want to be able to grab information out of, specific information out of other vectors and arrays, having this reproducible pattern can be super useful. So yeah, so grabbing information out of, let's say a vector, you do something called indexing, okay? And so we're going to show you exactly what I was talking about a second ago. So for indexing, you use the square brackets, okay? So this is one of the fundamental things you need to learn is there's 2 brackets that you use. No, there's 3 brackets you use all the time. We've introduced you to 2 so far. So we have the curved brackets, the parentheses, and so these are used for functions. Now we have the square brackets, and what they do is they identify a specific position within a vector or other data objects that we'll meet later on. And it allows you to just get that specific position, okay? What is going on in that position? So it really just allows you to grab information from vectors from a specific place. So here we have Z, and we want to go from 2 to 20 by 2. And so we've created this vector. And then what we do is we extract out, using indexing, we want to get the first entry in this vector. Okay, so we want number 1. So that means we're going to be extracting this. And you can see we get this back. Okay, we can also say we want number 8. So the 8th position of the vector. So as you can see, it's by 2, right? So there will be 16. And that's what we get back. So the square brackets, really important for getting information in and out. And so you don't have to use just a single number. You can use a much more complicated things. So here we have a vector to index another vector. Okay, and so this vector is 1 and 6. And so because we're using this to index the other vector, we're saying, I want to get positions 1 and 6 out. And so we get that out of Z, and we get this back. So this is a new vector we've just created, which is position 1 and 6 of the z vector. And then the other really important part is you can also use negative indices. And what a negative index does is it can be used to basically extract everything else apart from that one. Okay, so in this case, we care about position 5, but we specifically care about excluding it. We don't want to look at position 5 anymore. And so, because this is a by 2, that will be 10, and you can see that 10 is missing. So by using the negative 5, we get z back except for the 5th position. Okay, and so you may have caught it earlier, but I said indexing is really important for both extracting but also updating vectors, okay? And so what you can do is use the index to assign values back into the original object. And so this means you can update the object, but without having to update every part of the vector. You can update just a single part or just a couple. And so here we go back to our z. We have our 2 through 20. And we're going to say we want to update position 5 to not be 10 anymore. We want it to be 1000. And you can see when we now return z, we get 2 through 20, but 1000 in the middle. And so the way we're doing that is just by using our square brackets again to say we want to look at position 5, but then we use the assignment operator. So we're assigning 1000 into that position 5 of z. And so then this is where things can become very useful and interesting. If you remember, we have y. Y is 6 through 10. You can use vectors and variables on each other. So in this case, we're going to take the z vector, and we want to look at the positions that are detailed in y, so 6 through 10, and we want to update them to be 0. So then when we look at z again, we have our 2, we have our 1000, which we replaced, and then we have this 6 through 10, which are now all being updated to be 0. And so, as I touched on before, these are the two of the 3 brackets that we'll really get into contact with now. We have the square brackets and the parentheses. Square brackets, always indexing. Parentheses, always functions. Okay? Later on, we'll get to creating functions, and then we'll meet the curly bracket. But for now, these are the 2 you need to care about. Okay. So once you have a vector, as long as it's made up of numbers, you can treat it just like you would a single number. And so that means you can do arithmetic operations on it. So earlier on, we were doing like 2 plus 2 and things like that. Here, we can take x, which in this case, we've made it 1 through 10 again, and we can do x and multiply that all by 2. And what it's doing is it does it on a position by position basis. So it's not multiplying everything together. It is multiplying all the positions individually by 2. So this is really nice. And you can also add individuals together. Okay, so we can do x plus y. And because they're the same length, it recognizes that position 1 is equal to position 1, and it can add them together. Yeah, we just had a question in the chat about 1 through 10. I think Doug has it covered, but yeah, we just did this, what we just did here. We know how a better way to do this now, and that would be to do the colon and get rid of all of this. So just 1 through 10. Thanks, Doug. Yeah. And so this is nice because these two are the same length. Okay, so I mentioned length being important for this operation where we're adding them together, because it knows position 1 could go to position 1, position 10 can go to position 10, so it means 10 plus 20 equals 30, right? 1 plus 2 equals 3. But you can try and do operations on unequal vectors as well. And so here we have our 1 through 10 again. And what we're going to do is add this vector, which is a combination of 1 and 2. And so what it does with this shorter vector is it just recycles the values. Okay, so with the first one, it's going to add 1. With the second one, it will add 2. Third one, it will add 1. Fourth one, it will add 2, etc., etc. Okay. And so this is nice because we have 2. This is a length of 2 vector. And x has 10. So they're divisible by each other. So it'll just repeat it 5 times in its entirety. And so R is happy with this. There are mathematical reasons, or there are times when doing this is quite a normal thing that you'll be doing. This kind of division with unequal objects. What would be weird is if you're doing it with objects that are not divisible by each other. And so it lets you know if there's a problem, okay? It will still do it, but it will let you know that they're not multiples of each other. So here we have x, and then we have a vector of 1 through 3. And obviously, if you do add a vector that's a length of 3 to a vector that's a length of 10, it will do it 3 times, and then the final time you'll just have 1 entry left to fill. So you can see that here. It'll add 1, it'll add 2, it'll add 3, and then it'll get to the end and it'll just add 1. And so that's why it gets upset and tells you a warning, because your longer object is not a multiple of your shorter object length. Okay? So often you'll get these warnings as you go through. A warning means that it's executed the code, but something looked funny. Okay? You'll also get errors, and errors means the code wasn't executed. But quite often when you see a warning, that also means you really need to double check your code and be really, really sure that you want to do what you're doing, because it doesn't make sense. Okay, so that's what happens when you add together unequal vectors, or you do any kind of arithmetic on unequal vectors. And so far we've really been going through vectors, and we've been really focused on numeric vectors. But something else we're going to care a lot about is character vectors. And so, sorry, my mouse dry. So when you're working with character vectors, you can just pretty much use the same rules as you use for numbers. Okay, we use the C function again. But this time, for our characters, we're adding quote marks. So this really signifies that this right here is a character. If you don't put quote marks, it's going to think that you're looking for a variable. And if that variable isn't there in your environment, it's going to get upset. Alternatively, if you're trying to add a character that is the same name as a variable you have in your environment, it's going to add that in, and that might not be what you want to add. So say that you just put an x here, it will add in the x values. And that wouldn't be good if you just wanted an x. Okay. And so once you create here, we have these different characters. You can index them in much the same way, so we can get the second entry and it will return you Commonwealth. The nice thing about once they're characters, if you have some character vectors, you can actually assign names to other vectors with them. So in this case, we're going to redefine x as 1 through 3. And then we're going to use the function names. So you can see it's a function because we have the curly, or not the curly, the curved parentheses. And we're going to apply names on x. So this is our 1 through 3. And then we're going to assign to names. We're going to assign to names y. And so we know y is this guy up here, and that's our character. And then when we return x, we have our 1 through 3 here, just like you'd expect, but we also have these names associated with it. So naming vectors and also other data objects we'll meet later on can make it much easier for you to understand what your data is. It makes it much more readable to the human eye, and you can understand what's going on with your data. Quite often you can add, you'll have several observations, and you want to know which observation you're looking at once within your matrix or your data frame or even your vector. So adding these names is really important, and it's often with a function that says names, name, column names, okay? And all you'll be doing is using this function on the variable that you want to add names to, and then assigning to it. The other nice thing about once you have a name is it can actually make it easier to work with because you can use the names for indexing. So it isn't just about readability. It just also means, say you have a very large object and you're not sure. I don't know if Wolfson, in this case, is entry number 10 or 11. Well, that doesn't matter because you can just type this into your index here and it will grab it out. So here we're using a C. We combine ICTem and Wolfson, and we put them both into our indexing square brackets. So that means it's going to go into our named vector. It's going to look for which entries are called ICTem, which entries are kind of called Wolfson, and it's going to return them to us here. And so this is great. What can happen if you try and do this and it's not a name that's in here? So we're going to use strand. Okay, so you can see that isn't one of these names. We use strand and we get NAs. Okay. And so NAs, NA values are really important. They're what R uses as a placeholder when it can't produce what you're asking it to produce, essentially. There's no value inherently assigned. It doesn't use it like a 0 or anything because 0 has an inherent properties which might not be appropriate. And so, it uses this NA, which just means not available. The other one you might see is NaN, which if you perform a calculation and it produces a number that's not real, it will do NaN. So maybe you're working with logs or something like that, and you perform an illegal operation, and it will return NaN. Okay, so both of these are important because R has specific ways it will handle NAs and NaNs. And we'll show you how to handle them a little bit later. But they're really important placeholders that just kind of delineate there's an empty space here, or something's gone wrong in the math. Which stuff like this can happen, right? Especially if you're normalizing data later on and you have like 0 values and then you're doing logs and stuff like that. You will expect these to crop up. So an important function when it comes to both character vectors and numeric vectors is the unique function. And so I use this all the time. And so what it does is it helps you get any unique values from a vector. And so in here we have a gene list. we have gene 1, gene 2, gene 3, gene 4, gene 5, and you can see gene 1 and gene 3 are repeated. So you can produce, like quite often when you're like testing for significance, or you're comparing different lists and you're merging them together or something like that, you might get a duplicate here and there. And so by running unique, you can then trim away any of the duplicates, and you can get it back down to just the things that are unique. So it's a super useful function. Okay, so I think this is the last kind of vector we'll cover, and that's logical vectors. So logical vectors are made up, so we covered numeric and we covered character. Actually, there is a fourth kind, but that's a special kind that we'll talk about in a little bit. A logical vector are a class of vectors that is true or false. So you have these Boolean values like 1, 0, or true, false. And you can use either the full spell out true, or you can use a TF. Okay. Another one of these things is stylistically, you'll find that some people have preferences either way. I use them interchangeably, but if you're making like production level code, or you're making a package, they might ask you to fully spell it out. But that's a little way along the line. And so when you return, you save as a Z, or you save this as a Z. When you return this value, it returns true, false. Okay. And so just like what we did before with the numeric vectors, you can use logicals to index other vectors. Okay. And so as you may intuit, if it's a true, it will return the trues. If it's a false, it won't return the false. Okay, so we have a 1 through 10. We have interchanging trues and falses. And so it's going to return to us all of the odd numbers here, because we subset, or with the indexed with these Z. Okay, so generating these logical vectors is a really important way of subsetting your data. You'll be asking a question, is something true? And then you'll be able to get true and false answers on that. And so one of the key ways we do that is using the in operator. And so this is a percentage sign in percentage sign with no gaps. And what that's doing is you're asking, is values from vector A present in vector B? So quite often we'll be doing is, I have some genes of interest, and I've done a test. And so you can ask the question, are my genes in my test in my genes of interest? And what it will do is it will create a logical vector of the values in A, so my test, and they'll be true and false whether they're present in B, my genes of interest. So you can see that here we have our gene list, genes 1 through 5 plus 1 and 3 again. And then we can have a second gene list, gene 5 and gene 3. So this would be our test. These will be the genes that we actually care about. And so then we can ask gene list, is any of my gene list in my second gene list? And what it'll return is false, false, true, false, false. Yeah, you get it. And so this represents the third value is true, so this is gene 3. The fifth value is true, this is gene 5. And the last value is true, so this is where gene 3 is. And so we've created this logical index. We can actually then index this back into here and subset based on this. So you can see how here we're subsetting back out gene 3, 5, and 3, because they're the ones that were present in our gene list. So this is a super useful operator. Again, I use this all the time. Here we're showing a very simplistic example. But like I said, later on, you maybe have some significant genes, You have a list of significant, or a vector of significant genes, a vector of genes that are maybe to do with autophagy or something like that, and you want to know which ones from your significant genes are related to autophagy. And you can just use simple operations like that to subset it. Okay. And so the other way we can generate these logicals is from operators. And so this is what I mentioned before with the double equal sign. Oh, is there a way to find false indexes? Yeah. So if you ever want to reverse an index, you just put an exclamation mark in front of it. So in this case, if I put an exclamation mark in front of here, you can see my cursor, and I put it here, that means I'd get the reverse of that. Okay, can you determine what place in the list those genes are? Yes. So to do that, it gets a little bit more complicated. And we'd use things like a which operator. So let me think off the top of my head with this example, how we would do that. Okay, so let me grab this. I'm going to throw it into here. Actually, I'll tell you what we would probably do for this is we'd use match. Okay, so if okay, I was about to show you this, but what I'll do is I'll come back to this in a sec. I'll explain the next operator, and then I'll explain the limitation of the next operator, and then I can get to your question, Sonny. Okay, because that will make more sense, I think. Okay, sorry to hold you up, but I think you're just one extra step ahead of us. Okay. Okay, so if we want to ask a question, say of here we have 1 through 10, we want to know which one of these is equal to 5. So this gets to your question, Sonny, of can you determine what place in this list these genes are? We could ask a similar question here of like, which of these genes equals gene 5? Okay, and it will return a false, 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 true, false, false, which will give you the position. And to do those questions, what we do is we use the double equal signs, the greater than, or the greater than equals to, depending on what we want to ask. So the double equal sign is saying, are these the same? The greater than will ask, is it greater than, and then greater than or equal to, is it greater than or equal to? Okay, and so these are important for, these ones are more important for numeric vectors. And so in this case, you can see an example here. We ask, we have x is 1 through 10. We ask which ones are x greater than 5. Okay, and so you get back a ordered vector, right? And you can see the positions of which this is true for. Okay, and so this can start to get you the question of what place in the genes in your vector, or what place in your vector evaluates to be equal to or greater than. Okay, and then you can index with this. So we can index and we can get that back, right? And so you can also do more complex logical operations with this. So you can use an and so, or you can use an or you can use a reverse. Okay, so I mentioned the exclamation mark earlier. You chuck that in front of anything, it reverses trues to false and falses to trues. If you do, so here we use that here, x greater than 4, and it will give you everything that is not greater than 4. We can ask the question of x greater than 4 and also less than 7. And so that should give you 5 and 6, right? And so you can get that here. And then, last but not least, you can ask the same, but you put an or in. Is it greater than 4 or less than 7? And that should be everything. And so by combining these things, you can then do complex indexing. Okay, so in this case, we're doing this, and then we're actually indexing back out with these true falses. Okay, so to get now, we can go back to Sunny's question. Okay, can you determine what place in the list these genes are? Oh, I went the wrong way. So if this was just gene 5, this would be super easy, right? So if I switch to here, if this was just gene 5, I'll do this. So we have, I just ran gene list, and it's just gene 5. I could then just do gene list equals second gene list. And you can see it tells us that it's this position. Okay, the issue is if you have both of these, it's trying to evaluate two things. And so you get this kind of multiple thing about them not equaling each other. And that's because it's asking about gene 5 and gene 3. And that's not intuitive because it's looking for a match to both of these at the same time. And so what you can do is you can do more of the these AND statements that I just showed you. So let's do third gene list. Okay, so we now have gene list, second and third. Spotlight. So we can say gene list, we can get equals second gene list. Now we can do and I'll copy and paste this. We'll put third. Oh, no, we want or. Sorry, it can't equal both at the same time, but it could equal either or. Okay, so now you get both. And so you have the positions. Okay, which is, I guess, the same as match. Yeah, I don't know, actually. I think I just answered the question that we answered the problem that we already had. Okay, so you want a position. Okay, so you will need the numbers. Is that correct, Sonny? You want the position, the actual numbers as opposed to a true and false. So we could use which. Sorry, I went really the long way around there. So if you ever have a true-false logical like this, we just created one. You just put it in which, and it gives you the numbers. Okay, so which evaluates a true-false and turns it into the numeric equivalent of them. Okay. Oh, you're back at my big face. Okay, let's go back to the slides. Okay, so we have done vectors. There are exercises here, but we don't really have time to just sit around and you guys go through the vector exercises. But as a kind of intermediate, what we'll do is I'm going to give you a poll to see if you understand what we've kind of done, and strongly encourage you in your own time to go through some of these exercises. We will have a pause once we get through matrices. You can also go through it then, and I and/or team members will be around to help with any questions. And if you have any questions afterwards, you can raise an issue on GitHub. I also typically am around a little bit after the whole session finishes for the day. So if you want to take them on there, you can, and I'll be around to help. But I get that by then you might be quite tired because this is a long day. Okay, but anyway, so I'm going to chuck on a poll about vectors. And then I'm going to go grab my power cord for my laptop. There should be a couple of answers that are true and a couple of answers that are false. So I want you to tell me which ones are true. Okay, I'm going to end the poll. Can people see the whole text? Because that could be an issue. Let me just get the chat back up. So with question 2, are you able to see the end of the question? All right, so let me share the results first. There you go. When you were answering the question, could you see the end? Okay, so it might be system dependent because it seems that some people could and some people couldn't. So that might make it harder for some of the questions, and I apologize for that. I didn't realize I assumed it would wrap the text. So that is my bad for some of the people in other systems. So if we quickly go through this, let me just check how we're doing time. Okay, so we just have this to do before midday. Okay, we're on good time. So let's go through them one by one. So question 1, which of these is true? They can contain logicals. True. I think we just saw that they can have logicals, and I think most people got that. That's trues and falses. The next one, they can contain characters and numerics and this would spell out to say same time. Okay. And that isn't something I explicitly explained. So I get why we have a relatively large population of people that have put true for this. And we're also missing the end, so it must be hard to read. But vectors can't have characters and numbers in a vector at the same time. Okay, if you have some characters and you put some numbers in there, it will turn that into a character. And so what I mean by that is, if you have some names and then you add a 1 onto it by using combine, what it will do is it will convert that into a character. And so then you won't be able to use that number to index anymore. It will consider it to be essentially text. And so this is a really important note, and it's something that's also going to be true of matrices. And so there's specific data types that can handle both at the same time, but there's specific data types that can't. And so this is a key consideration when you're deciding which data type you're using in your project and your analysis. Okay, we got one person who fell for the curved brackets, parentheses. And so if we remember that the golden rule, parentheses means you're doing a function. Okay, and then everyone was pretty strong on square brackets is indexing. Okay, so this is a key rule. Most of you got it, and hopefully now the one person that didn't get it will get it in the future. Okay. So it seems like we're on fairly good tracks. And so what we can do now is we can get into matrices. Okay, so we've got just over half an hour to cover some matrices. I think we'll have easily have time to go through the matrices in that time, and then we'll be having a break. Okay. So what is a matrix? So most of you probably use Excel or Google Sheets all the time to take in data from the bench. And yeah, Excel is great. But we can create a lot of these similar kind of data tables in R. And so this is what the most basic form is in R is a matrix. And it's basically a vector, but it has 2 dimensions. That's the easiest way I think about it. It has a lot of the same properties of a vector, but instead of it just being this 1-dimensional array, it's a 2-dimensional array. And so when we want to make a matrix, we can use the matrix function. Okay, remember function, so parentheses. And the first argument in a matrix is what you want to go in the matrix. Okay, so in this, we're saying we want the numbers 1 through 10. We want this number of rows. We want n row to equal 5, and we want n col to equal 2. Okay, we save this as our narrow matrix by assigning. And then we look at the result when we write this back out. And so you can see here that we have 1 through 10. Okay, so 1 through 10 has been added. It's been added in a column specific way. And you can see, yeah, we have 5 rows along here, 2 columns. Okay, so 1 through 10 has been added. It adds first column, then it adds second column. Okay, then we can switch this up. So again, we create a matrix exactly the same, but we just switch what row and what column. So we have 2 rows this time and 5 columns, and you can still see it's filling by column 1, 2, 3, 4, but you can see it's a wide matrix now. So you can see I made great pains to make it clear how the data is being entered into the matrix. So I've been talking about it's been going by column. There is an argument you can add, which is by row. And so that will pivot it around and it'll enter it in by row. So this is important because if you say you have a very long vector and it contains all your data in it, but it actually is 2-dimensional, if you want to build up a matrix from that, you can then build it up and fill in the data using that vector. And so with vectors, we were using the length function to get some inherent properties of the vector. But it's a little bit more complicated for matrices, right? Because you have several dimensions. So we have an extra couple of functions for that, for matrices. So the first one is dim. Dim is probably the most useful one because it gives you both the rows and the columns, okay? But if you are just interested in the rows, you can use n rows. So this is number of rows, gives you 5, or number of columns, get back 2, okay? All of these are, you'll find when we get into using things like loops, you'll find out you use this actually quite a lot. Okay. And so, as I mentioned earlier, a matrix is pretty much just like a two-dimensional vector. And in that sense, you can easily create a matrix from vectors. And to do that, you use the cbind function. Okay. So cbind basically means column bind, and you're binding together different vectors as columns. And so in this case, we have x is 1 through 5, y is 11 through 15, and z is 21 to 2. We can then c-bind x and y together to create a matrix, and you can see it's created here. Okay, so we have these two vectors. They would be one-dimensional, but because we have c-bind, we can stick them together and we can make a matrix. We can also do this with r-bind. Now, as you can probably guess, c-bind is for columns, r-bind is for rows. So we created z, which is 21 and 22. So if we r-bind this onto our matrix we just created that had two columns, it will just fit right nicely on the bottom here. Okay, and so it's important to remember with these r-bind and c-binds, the order of operations of the vectors and matrices that you put into these actually governs the ordering that they come out in the output as well. So for r-bind, whatever is first will be on top, and whatever second will be on the bottom. Likewise, whatever goes in first will be the first column, second, the second column. Okay, so something we talked about with vectors and arithmetics is unequal sizes. Okay, and so you can imagine cases like this with c-bind, right? If you try and c-bind things together which aren't the same length, or if you try and create a matrix with data that isn't the same length as the matrix you're creating, that could create problems. And so in this case, you can see here, we have matrix, and we're entering in values 1 through 5. So we have five data points, but we're creating a column, 2 columns, 3 rows. So we have 6 places we can put those 5 data points. So what it does in R is it recycles again. Okay, so it'll go 1, 2, 3, 4, 5 with recycling, and then it gives you a 1. Okay, so it's reusing the 1 again. And again, it will give you this warning. So again, pay attention to your warnings. If you ever get a warning, it means something doesn't look quite like right. It's only a warning and not an error, because sometimes you want it to be that case, but more times than not, a warning is a bad sign. And so we can use a similar thing with r-bind, right? So we just create this matrix. It has 2 columns. And what happens with this is it actually clips. Okay, so most of the time, if you use c-bind, you use matrix, it does this recycling thing. With r-bind, it's different, and it actually clips. And so by this, we mean we had 2 columns in this one. We're adding a vector that is length of 5. And you can see that it added the first 2 values and nothing else. If it was recycling, you'd almost imagine there'd be a 3, 4, 5, and then this top half would be repeated. But it doesn't for r-bind, because it's a bit more complicated. And so it gives you another warning that the numbers don't match up. And so this is something you need to be really aware of, because you could be losing data here, right? Like recycling is one thing, like you're adding data that isn't necessarily there. You're recycling things, but losing data would also really, really suck. Okay, so there's something to be aware of when you're playing around with these matrices and these vectors, adding them together, manipulating them. You can do these things that will trigger a warning, but it will evaluate. And so you just have to be very careful and really just keep an eye on what your matrix looks like, keep an eye on what your vectors look like, and make sure they make sense. Okay, so names. As I mentioned before, there's lots of different ways to name. We saw naming with vectors, and I mentioned at the time that there's col names and row names and other name functions. And so this is where we get to use them. And so in this case, we're creating another matrix. It's 1 through 10, 5, 2. So it's the same as our wide matrix we created earlier. And what we're going to use is this function called paste, okay, to generate some names. And so what paste does as a function is it will paste together strings, okay? And so in this case, we have a string here, column. We actually have a vector, so 1 through 5. And we also provide a separator. So it's going to stick these together, and the separator is how to space them apart. Okay. Paste can accept a ton of arguments. So I could add in lots of other things here, and it will just keep concatenating them together. But the nice thing it does is once you have a vector in it, it's going to, instead of sticking them together like column 1, 2, 3, 4, 5, it's going to go column 1, column 2, column 3. It's going to vectorize over the vectorize the function, and so that means it will apply it to each point in the vector individually. And so this is a nice way of using paste. Can be a really nice tool for building up indexes and things like that for which you name a matrix. So here we use paste, and we're doing it on 1 through 5, and we have this separated comma, and you can see this is what it produces, and we're assigning it to our matrix using col names. So col names is the function for column names, and then we have the same for row names. We do a similar paste operation here, and we get this named matrix back up. And so the nice thing, which I didn't show you before with these names functions, is once you have a named object, if you don't do the assignment and you just use the function by itself, it returns you the names. Okay, so we have our named matrix, we call col names, and it just tells you what the column names are. And so with our named vector that we used before, if we just use names on that, it will tell you what the names are. So for any of these kind of name arguments that we'll meet as we go, anytime you're not assigning to it, you're basically giving it the opportunity to actually respond and echo back what the names are. Okay, indexing. So as you imagine, indexing is very similar. I keep reiterating this point. Matrices are just like vectors, but two-dimensional. They're very similar, but it's obviously going to be a little bit more complicated because you have to think about an X and Y, not just position, okay? And so the way this works is you have your matrix, you have your square brackets, and then you will have two different index points, okay? And these are separated by a comma. So this will give you your XY coordinate essentially within your data, in your matrix. So we can see this in action here. So we have our narrow matrix. It looks like this. If we want to get something from the first column, but the second row, okay, we're always going to remember it's row, then column. So we'll use number 2. And then first column is this one, okay? So this will go second row, first column, and you get the number 2. You can also just not supply a value if you want to get the entire row or the entire column, okay? So in this case, we are leaving the row index empty, and we're saying we want the second column, okay? So we get 6 through 10 back, and if we look back, this is the whole second column, okay? And because we're extracting just one column, it becomes a vector. Okay, so this comes back as a vector. Okay, likewise, we can do it with just the row. So in this case, we leave the column empty. Okay, and so we're just getting the third row. And again, this is one-dimensional now, one-dimensional data, so it becomes a vector again. Okay, so we're getting the third row and we're getting this guy out. Third row. You can also index again using vectors, okay? And so you can index to get more complicated things. So say you want 2 rows at a time. So in this case, we want the second and third row. We use the C to combine 2 and 3. Okay. And so again, this is the C function, so it's parentheses, but then we're using it to index, so that all gets wrapped up in a square brackets. Okay, so we're getting the second and third row. And so now it's, even though we're indexing out of the matrix, we are extracting out 2 rows, and so it's still going to be 2-dimensional, so we get another matrix back. And so you can see 2, 3, 7, 8, and if we flick back, second and third row, we just got 2, 3, 7, 8. Cool. And then once you have a named matrix, you can index using the names just like anything else, okay? So like we did with the vectors, if we have our col names, we have our row names. Now we're going to take the narrow matrix and we're going to extract out column 1. Okay. We can extract out row 1. We can extract out using both. So again, this is, it's slightly more to write and is less useful if you have a small matrix, but when you have a really big one and you don't want to have to track down which column is, I don't know, your gene counts, and which column is your length, or which row has your beta-actin gene in, being able to just have the names makes things a lot easier. So vectors, again, matrices can work with, can be subset by logical vectors as well. A lot of the indexing works in much the same way. It's just you have to consider both X and Y in this, okay? So in this case, we're going to extract out from narrow matrix, we're going to extract out column 1, okay? We're going to ask the question, which of these is less than 5? Okay, so we've turned it into a vector. We're asking which is less than 5. We find out that the first 4 rows are less than 5. And then we can take that and we can put it into our indexing. And you can see it's dropped the 5th value here. Okay, so this is getting a little complicated because it's a little bit nested, but we can start at in the inside just to make sure. So what we're first doing is grabbing out the first column. We're then asking which of them is less than 5. And then those true and false values are going into the row section of the indexing. And we're asking for all columns here because we're not putting a column value in. And then we index back out of the same matrix here. Okay. So that is using logicals with the matrix. We can also, a lot of these, it's going to be a continual thing. These rules will keep applying. You can also use math, right? So we can subset out specific points and add 2. So we're subsetting out the first one, position 1, row 1, column 1. We're going to add 2. It's 1 plus 2 is 3. We can take out an entire row. So we'll take out the first row. We'll add 2 to that. You can do it to the whole matrix if you want. or you can perform more complex like operations like doing a mean. And so in this case, we're going to do mean, we're going to do the whole matrix, and it returns you to the mean to the whole thing. Okay, it's super easy. So like as long as you have a numeric matrix, you can use all these arithmetic super easily. Yeah. The indexing works in much of the same way, so you can replace elements. So you just have to do the same indexing that you wanted that we have been introduced to, and then you use the assignment operator. So in this case, we have our narrow matrix. I'm going to say that position 1, so row 1, column 1, I'm going to put a 10 there, and I'm going to assign it there. Or I could actually do a replace for an entire stretch of numbers, just like we did with the vector. And so in this case, I'm going to replace the entirety of column 2 with 1. And you can see the result of that here. So I'm replacing row 1, column 1 with 10, and the entirety of column 2 with 1. Okay, so something I touched on before, which is similar to vectors, is they have to be all of one type. Okay, and this is going to be different from the data type we talk about, I think next, which is data frames. So if in this case we have this is our narrow matrix, it's all made of numbers. We can do arithmetic on it. We can multiply it by 2. It's a numeric matrix, right? If we were to do a replacement, so we're going to replace row 1, column 1 with a character. So in this character is called not a number. Okay, you can see it's a character because we have the quotation marks. Once we do that replacement, we can look inside and you can see that everything now has quotation marks, even the numbers. So that means it's converted everything to a character because it can't handle both at the same time. And so that's a key thing to remember with matrices. And so that means if I try and do math with it, even though none of these values in column 2 has changed as such, it will now not work and it will say there's a non-numeric argument. Okay. Cool. So that is matrices. What I'm going to do is throw up another poll for matrices. Okay. While you do that, okay, so this is just going to be a similar true, false, what is true and what is false with matrices. Okay. While that is going, we have a question from Amichai. I hope I pronounced that correctly. Is there something like undo in R? No. So it depends what you're doing. There are ways to help prevent you having issues. But broadly, once you do something in your environment, say you manipulate a object like this. Say you do this and you accidentally turn your matrix into a character and you don't really want it to be a character anymore. What you'll have to do is generally go back and redefine that matrix. The nice thing is, if you're in RStudio, it will save your history. So you can get all the code that you used and rerun it. Another key thing I'd say is what I do is all of my code that I run, I have saved. I run what's called an R Markdown document, which I'll introduce to you on Wednesday. And so this means that all the code that I'm running is present, and I can just press a button and it will rerun it all again. And so that means I don't necessarily, like if I make a mistake or I do something that does something weird, I can refresh it all and it will be okay. But yeah, you can do things that permanently change your data in the environment. Okay, but okay, yeah. So this is a really, really good question. So if I make a matrix, a character matrix, by replacing one numerical value with a character, can I make that value numerical again? And then will that make other values numerical too? There is ways to do this, but in this exact workflow, it will not work because characters kind of override a numerical. At this point, once you've created this thing here, it considers all these other values to be characters as well. So even if you replace this with a 1, it won't recognize these as also potentially being numerics. Okay, but what we'll introduce later on is this concept of coercion. And so what happens here is when you add this coerces all of the other your other data points into being characters. But we can also do that manually ourselves. So what you could do here is you could turn this into a character called 1, right? So you could use a value similar to this right here, and then you could use this function called as.numeric. And so what that does is it'll manually convert the type from character to numeric. Okay. This works pretty well, but there are times where it gets upset with there's some coercions that don't work as efficiently as others. But for this specific example, you would be able to step backwards using that way. Okay, we have another question about naming matrices. Do you have to specify the? Do you have to have specific number of columns and row in? Oh, okay.
Yeah, I mean, I'm just easier to speak than type here.
Yeah.
So I was just, I mean, this is kind of flowing kind of quickly, but while it was all happening, I was playing around with naming the columns and rows in the narrow matrix. And if I didn't put the number of columns or rows in the parentheses, then I got an error, right? So I had to specify that it was a matrix with X number of columns and Y number of rows to get it to append the column and the row names. Maybe I'm missing something.
Okay, I think I'm still a little confused. So I think you're asking. So correct me if I'm wrong, but say
I can make it really clear if I just paste the syntax.
Yeah. Paste that syntax.
Yeah. So you see, it says column, then comma 1 to 5, for example, because that was the number of columns in the particular named matrix in this example. In my narrow matrix, I only had 2 columns, and I had to specify comma 1:2. But if I just want to name all the damn columns, regardless of how many there are, is there a way to just skip can you skip the syntax of defining the column size?
Yeah. So this is a really good question for when it comes to things like automation. So let's say we have our matrix. Sorry, I have to kind of like write some of it out because, oh, that's not matrix. Because I can't copy and paste from the chat, I don't think. Oh, maybe I can. Will this work? Oh, okay, cool. We have that turned on. Good. Okay, so if we just look at this is, I think, what the issue, right? So we now have, when you do just paste column 1 to 5, you've created a vector of characters that is 5 long. Okay. And so now, if say we have our named matrix, okay, this looks like this. say I wanted to use this to actually name my rows. Okay. So this is empty at the moment, but we know it's too long. Okay, so if we did n row, you can see it just above here. There's 2 rows. And so it's going to get upset. Oh, no, if I do row names. And then I assign the columns to this. So remember, this is 5 long. Going into a container which is too long, it gets upset. And so that really is just an issue of unequal lengths. Okay, and so we've seen, depending on what it's doing, what question you're asking, it will solve that for you, and come up with ways like recycling and things like that. But in this specific case, it just errors. Okay, because most like naming something is a very user-directed thing, and it's not like mathematical really. And so there is no intuitive way that R can think of that you'd want to put a vector of length 5 into a row names of length 2. And so really, in this specific case, if you just had this vector and you just wanted this to work, you could just do 1 to 2, right? And you're at this point, you're just saying, I want to get the first 2 and put it in, and that's fine. Okay. And so now you've got, for whatever reason, we have column 2 as our row, column 1 and column 2 as our row names. Now, if you wanted to do this in a more intuitive way, so a way that actually adapted to your data, what we could use is ncol or nrow. So you could put nrow in here and your named matrix. And now it's gonna do it 1 to 2, but now if we do make our named matrix, let's say it's 100, it's going to do it 100 times because it's reading in the properties of your data directly and just determining the limits based on that. So a lot of the times you can use like this nrow, ncol to actually contribute to determining how you name things, how many times you maybe want to, if you want to do a loop or something over your data. These properties then become really important for setting the limits for that. I hope that made sense and answered the question.
Thank you.
Cool. Right. So I'm going to, like, the poll's been running for 10 minutes, so I'm going to end it right there and quickly go through the answers. Okay. So which of these is true for matrices? They can be combined with the C function. That is wrong, unfortunately. So the C function is for combining vectors. If you use the C function on a matrix, okay, let me share the results. You want to be using C bind and R bind on a matrix. Okay. I think, let me double check. Let's see what happens. Okay, let's make a second matrix, named matrix 2. Okay, so you can see what happens there. Yeah, we have the feedback in the chat as well. So what it's basically done is taken the 2 matrices and convert them all into a single vector. Okay, so C really is about vectors, and it wants it to be a vector, and it will make it a vector if it's not a vector. Okay, so C bind and R bind are your friends for matrices and any 2-dimensional arrays. They can contain logicals and characters. They can contain both, but not at the same time. Okay, so this is my poor phrasing by not saying at the same time. So I intended it to be at the same time. Okay, but as long as you're thinking they can contain logicals or they can contain characters, you're good. They have 2 dimensions. You guys have got that, and they're indexed with the square brackets. Cool. So most of you got that as well. And so the key point with the square brackets in this case is they also use the comma. Cool. So it seems to be going well. You guys are mostly getting to grips with this. So what we're going to do now is we're going to have a little break. We're going to have an hour, and then we're going to come back and we're going to talk about some more different data types. We're going to get into factors, data frames, and then reading and writing data. Okay. And so we'll start that at 1. We'll do that for an hour, and then we'll have another hour-long break, and then we'll come back at 3 to finish off with the rest of what we'll talk about today with R. And that's really using operations to really speed up your data analysis through things like loops and functions that are called apply. Those are the big ones. Okay, so any other questions? If you want to play with the exercises as well, they are all in the presentations. But I'm sure most of you probably just want a break because you're fed up of looking at RStudio for 2 hours. But we'll be back in an hour. Okay, I'm going to pause the recording. Okay, and then I just need to reorganize so I can see the chat and everything again. Actually, I think I missed one. I had a question that I missed during the break. But I don't think they're here anymore, so I'll just email them. Yeah, Sadia had a question about the organization of RStudio, but I think I can directly address her question to her or them. Okay, so what we're going to do is get into factors.
I can tell you the questions if you want to address them now, or I can ask you later.
Oh, you're here. Okay, great.
So the first question was about how could we confirm that we actually did set up the directory as intended? Is there a way to check that? And then the second question was about the RStudio interface. What was the difference between the top leftmost panel and the bottom leftmost panel? Did it matter which one you used? So I'm brand new to coding. I know nothing.
Yeah,
but
yeah.
I followed along everything, but yeah.
No, that's cool. That's cool. Okay, so let me just, I'm going to switch into my RStudio window. Okay, so how do you know you're in the right place? Okay, so I think I showed you, you can use set DW. Okay, so you can use git DW. That tells you which working directory you're in. Okay, so at the moment, I'm all the way down here. I'm inside Intro to R, and I'm inside R course. Okay, so when you download this, you should see, and you navigate with set, you might navigate with set WD. Okay, so this is will just allow you to navigate to where you want to be. So I could go up 1, and now I do git WD, and now I'm in Intro to R one day, and I'm up 1. We want you to be in R course, so I can just do set WD R course. Okay, and you should be able to know that you're in this because if you do the dir command, which you saw earlier, you should be able to see presentations, you should be able to see exercises, you should be able to see scripts and data. The other way to do is, like I showed you before, is when you do git WD, this whole section should be where you downloaded it. And this section here should be the same. So it should be Intro to R one day, and it should be R course. Or it might be Intro to R one day with some extra appendage here, like master or something like that, or some numbers. But it should say Intro to R one day, blah, 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 blah. And then you can navigate into the R course folder within that. And so this means when you look for folders from where this working directory is, everything is relative to this position. So if you look for a file, you can look for a file within data and it will find it. So I can just say, if I want to see what folders are in, what files are in data, I could do dir data, and it's going to tell me what's in data. But yeah, so this is very much like the working directory is like the viewpoint on the rest of the computer. But you can practice to get an idea of what that means a little bit more by using setwd for setting the working directory, getwd to see where you are, and dir will tell you what's in there. And so then your next question is, what's the difference between this left and the top left and the top left and bottom left? Okay, and so the bottom left is your R console. This is where the code is being evaluated. And so you can see with the way I'm interacting with it, right? This is where I'll put my function. But this up here is where I'm saving what I'm doing. So this is essentially like a little notebook. And we'll tell you how to use this more effectively on Wednesday when we talk about R Markdown and things like that as a way to generate real reports that you then can share with people and say, I did this analysis and I used these packages. But for the moment, what we have here is just some code that I used, and this is where I would often just write stuff, and then, but it won't be evaluated until I like copy and paste it and put it down here. Or there are shortcuts to do things like run. You can press run and it'll run, or control enter if you're on a Mac, and then it will run directly from here to here. So you can then save this document, and this is just basically it's just some text, free-form text notes, but nothing has been evaluated in R. This is not in your environment, but this is the thing you're actually interrogating. You're throwing it to R, and R is throwing you the answer back, or you're saving something into an environment here. This is the actual activity. I hope that makes sense and answered the questions.
It does. Thank you very much. Appreciate it.
Cool. Right. So we are now going to talk about factors. Okay. So we talked about how there are different types of vectors. We've talked about logical, character, and numerical. There is an extra type of vector called a factor. It's very special, and it can be very, very powerful, but it is a little confusing when you start. So factors are used to store categorical data. So something that has clear defined categories when you're collecting it. And so this generally isn't super great for continuous numbers and things like that. But it can be very good and very useful for if you have specific categories, like whether you're working with male or female or other, for example. So to create a factor, you use the vector factor, or the function factor. And we can take a vector, we put it into factor, and it will turn it into a factor. Okay. And so the real difference between a vector and a factor is it now incorporates these things called levels. Okay, so let's have a look at this. So we have our vector here. We have male, female, female, female. We then save this as our vector. We then put that vector into the factor function. And we've created a factor here. And so now when we return this, so this has been entered into the R console, and we get back there's male, female, female, female. So this looks just like a vector, but now we have these levels. Okay, and so you can get the levels of a factor back by just using the levels function. And basically what levels are doing is saying, these are the different categories within my vector. These are the different options that it can fit. And everything has to be one of these options. And so an example of how powerful it is to have these levels encoded and is kind of like restricting the options of the vector is when you use a function called summary. So summary is a really nice tool because it basically takes whatever data type you give it and it tells you some information about it. And And so if we take this vector example, it will tell you it's got a length 4, its class is a character, its mode is a character. So we right here, the vector example, it's a character vector, and it's got 4 length. If you do it to a factor though, it actually starts to tell you about the data itself. So it tells you you've got 3 female and 1 male. And so this is why factors can be useful, because it can start to allow you to aggregate the data a lot quicker because there's less options. When you're working with factors, by default, they get displayed in alphabetical order. But you can change what the defaults are by actually encoding the levels when you create the factor. So here we say factor, we have our vector example. But this time we're actually going to say these are my levels. Okay. You can also include other levels as well that aren't in your vector. And so in this case, we're saying actually we want male first, then female. And then when we create the factor, you can see in the levels, male appears first in the levels. And then when we do the summary, male appears first. So this hierarchy and ordering in the levels actually is an inherited characteristic that is important every time you want to do any kind of this summarization. And most importantly, for most of you, is when you want to do plots. So if you want to do it like a box plot or a bar plot for this data, the ordering of the columns is dictated by the factor levels. So by making sure your levels are correct, you can then make sure your plots look good and are ordered in the way you want. Okay, and so beyond this, there's also another level of ordering where you have, there's no kind of, like it says, there's no natural order to the categories, as in one is not bigger or greater than the other. So in this case, we can look at the levels and we can ask the question, is number 1 less than number 2? Okay, and so we're asking this question, is male less than female? But it's not meaningful for factors, and it knows that, okay? And this makes sense, right? Because this is also, it's a character, right? So if you did this with a character vector, it would respond the same, because there's no inherent, this is bigger than, greater than, better than, okay? However, what you can do is add ordering. So here we're saying ordered equals true. And so this means even though this is a character for small, big, it knows that small is less than big. Okay, so the order of the levels, so the fact that in levels we say small first, then we say big, and the fact that we're saying ordered equals true, means that it knows that small is less than big. And so then when you look at the factor example, which we just made and saved, you can see it in the levels. And so it can say small is less than big. And then if you have a factor example, we take out number 1, we take out number 2, and then we ask it the question, is it less than? It can actually evaluate that and say it's true. And so in this case, it's asking, is small less than big? And so this is another strength of factors, is you can add these extra characteristics to the different levels that you can't do with, say, a character vector. That said, this does make things more complicated. You can't just replace a level you can't just replace an element in a factor with something it hasn't seen before that it doesn't know anything about. So in this case, say we want to replace the first value in factor example with big, okay? We're going to do that here. So the first value is small. We're going to take our indexing. We're going to take the first value and we're going to replace it with big, and it's happy, okay? You can return factor example. It's replaced it, no problem. Now, if you try and do this and you replace it instead with the string huge, you get this warning. invalid factor level. And so then when you look at your factor example, you get an NA. So we've met NAs before, right? And they just mean there's not it's an empty vector, an empty position in your vector. It is, for whatever reason, it can't figure it out, so it made an NA. And that's because the levels, there's not an option for huge. And so it has no properties for huge. The factor doesn't know what to do with huge, and so it just turns it into an NA. But what you can do is you can update your levels. So by using the levels function, you can then open up this for assignment. So you say, we want to look at the levels in our factor example, and we want to assign big, small, and huge to be levels in this. Now, now that huge is one of the levels, you can then assign huge to number 1, and it will remember it. So okay, so in this first question, so I got a question from Amichai Berkowitz. Why do I need the word C before huge? Oh, I see. Yeah, that would work. It would be fine. So you could drop the C in this case if you wanted to. Yeah, so sometimes when you have a vector and it's a single entry like this, or in big, the case of big, you don't necessarily need to wrap it in a C. We often include it in the training just because it visually helps you realize that it's a vector. But you don't actually need to have that for it to work. Okay. Okay, so we're going to do a quick poll now on factors. There's only 3 options in this one. And again, tell me what is true about factors. And we'll just do it for a minute real quick. All right, we'll do 5 more seconds if anyone else is doing it. Okay, so let's share the results. It seems that most of you got the first one. So they store categorical data. That is the whole point of factors, is you have these categories that are predefined that you'll want to allocate your vector into. So whether it's small, big, huge, that kind of thing. So these are actually, these are really useful for things like metadata in studies, because you normally know what the options are for your metadata. The number of levels is the length of the factor. No, because you can have, in our case, we had a vector that was about 5 long, and we had 2 options, small and big. And so there was 2 levels, small and big, but there were 5 different entries in the factor. So that means the length was 5. So they are not necessarily equal. It's easy to replace elements in a factor. This is, I guess, all down to personal feelings about this. I find it's harder to work with factors because it is harder to replace elements in a factor. That said, it's just one extra step, and it is still relatively straightforward. Once you follow the rules that we talked about, you just have to increase your levels, and then you can start finding and replacing with whatever new thing that you want. Okay, so data frames. So this is where most of the action happens with regards to your data analysis. Most of the time, you are going to be working with a data frame. Okay, and so what is special about a data frame? Well, it's very similar to a matrix, except instead of with a matrix where you can only have one type of element in it, you can only have characters or you can only have numeric. This allows you to have multiple types. And so each column can be a different type of data. So in this case, we have an example, we have some names, and then in column B, we have some characters. In column C, we have some numbers. In column D, this could be a factor, for example. And so to do this, we use the function called data.frame to build them. And so here we are building, we have a character vector. You can see we're using C, and we're doing patient 1, patient 2, patient 3, patient 4. We have a factor, and that is made up of, we're using rep, which we met right at the beginning. So rep is going to repeat this vector, male, female, twice. So we're going to get male, female, male, female, which you can see here. We're going to have a number for survival time. And then what we can do, we put this all into our data frame, data.frame function. And while you're creating your data frame, you can create column names at the same time. So the first column, we want to put the patient name data. And so we're going to say name equals patient name. And so what this means is the first column is going to be called name, and it's going to contain all the data from patient name. Likewise, the second column is going to be called type. You can see it here. And it's going to have all the data from patient type, and survival time going to contain the data from survival time. So this is a nice way to build up an annotated data frame as you build the data frame itself. And so then when we do this, we have df example, and you can see we now have a mix of data types. They're all encoded within it. It knows what type of data each of this is. And it all has the column names. Indexing works in much the same way. So remember, when we index, we use the square brackets. And so in this case, we're going to be asking, we use a logical. So we can say we're going to index first by survival time. So we're going to get the column survival time out. We're going to ask which of these is greater than 10. And then we're going to put this into the row of df example to extract out specifically the survival times that were greater than 10. So patient 2 and patient 4. So that's kind of a complex indexing, but you can see how you can use these different levels of indexing in much the same way as we did for matrices. It's just the key part is, right, you have the 2 entries within these square brackets separated by a comma. Okay, and you can have an empty entry, and that means you're getting the whole row or the whole column. The nice thing about data frames is there's alternative ways to do this as well. So if you know the names, you can also use a $sign. And so what the $sign does is it allows you to extract out index a column using its name. So in this case, we can use $sign survival time, and it will extract out all the information in that column. And then we can perform a similar operation as we did before, right? And it works in much the same way. As it's doing much of the same thing, you might ask, why would we do this $sign thing? Well, the nice thing about the dollar is it will autocomplete, okay? And this can be good in 2 ways. If you're writing out this value right here, df example, and you do this, you can press tab, and what tab will do is it will bring up options. Okay, and these options will be the list of options from your column names. So tab to complete is really nice. But also, you don't have to fill in the whole thing. It will just figure it out from just the beginning. So you can just type in SURV. As long as there's a unique start to a column name, it will know which column you mean, and it will just complete it for you. It knows that all you need is this, and that means the same as this or this. Okay, so you can just, as long as it becomes unique, it will know which one you mean. That said, if you did it this way with the square indices, if you only put in part of the name, it won't work. So these little tricks can help you speed up coding a little bit. The other nice thing is you can actually create new columns this way. So in this case, we're going to create a new column. Okay. So we use $, we put in the name we want for this new column. And in this case, we're just going to repeat in new data the number of times that's equal to the number of rows we have. So in this case, it's going to know that we have 4 rows. So it's going to repeat the character new data 4 times. And then it's going to stick that into our new column here. And so now when you look at it, we have a new column with 4 entries, all of them saying new data. So this is nice because it allows quick and easy access and interchange of information with your data frame. Replacement you can just do replacements in pretty much the same way. So in this case, we're doing a bunch of indexing here. This is quite complicated. I can explain it step by step. So we're asking which rows have a survival time of less than 10. Okay. And so that will be row 1 and 3 because their survival time is 1 and 2. And then we're saying specifically we want to focus on the column that is survival time. So we're going to follow on the survival time column and we're going to focus on 1 and 3. And then we're going to assign a 0 to them. Okay, and you can see the output of this. So we now have 0s in survival time, and where previously there were a 1 and a 2. Okay, so this is exactly the same as we did with the matrices, with the vectors. It's just a more complicated example. Very similar to when you work, like if you're doing it with a factor, right? You are still going to have to update the levels. Okay, so even if your factor is wrapped in a data frame, you're still going to have to work with it like it is a factor. And so in this case, our factor is the gender. And so we have male and female, and we want to update one of them to be other. But it's warning us that it's an invalid factor level. So we need to increase the options in the levels. So we have our data frame example. We can do the levels of this column. So type. We can do df example. We can take the levels of the. So the way we're doing this is we're taking. We're going to be assigning to the levels here, but we're actually going to use the original levels in the assignment, and we're just going to add the option of other. So we're combining here the levels we have already with an option for other. And then we're assigning that back into levels. Okay. And so that means the levels have been updated. This is a trick we quite often use if you want to just update the levels, but just add a single entry. You just use the same levels on both sides, but you're just going to add a C and add an additional level. And so now we've increased the options to other. We can then assign other into our first row, our first entry. And so you can see here we have other. something to be wary of. It's so our data frame is just two-dimensional factors. No. So if you remember when we built this at the beginning, okay, specifically, patient name is a character vector. Patient type is a factor, which is a type of vector, but it's a specific type, if you remember. And survival time is a numeric vector. So we have these different types. And the big thing with data frames is it can contain all of them at the same time. Okay. So any of the assignment like this assignment works fine, but it's just because we're updating a factor. Yeah, so for you guys, it's going to be less of a problem now. But if anyone runs into anything from R that's prior to version 4, so if version 4 came out of April last year, if any of you are running 3.5, 3.6, or go on a machine with 3.5, 3.6, or even look at answers someone's giving to a question, and it's an older version of R, by default, when it creates a data frame, it does turn everything that is a character into a factor. So Greg's question there about, is a data frame essentially a two-dimensional factor? It used to be much closer to that. And it would be a case that every single thing that contains strings was read in as a factor. And this created all sorts of issues. It was like, factors are obviously great, but a lot of the time you aren't wanting to work with factors, and then converting from a factor back to a character is a real pain. So the defaults have been changed. It used to be that when you read it in, if you had data.frame, the default would be strings as factors equals to true. It now defaults to false, so you don't have to worry about it. But if you're working on an older system and it becomes an issue, you can just add this parameter in, and you should be good. Yeah, and so this is just an example of that. You can switch it to strings as factors equals false, and it allows you to update things easily. Okay, so a very useful function is the order function. Anytime you have a numeric vector, this can become super, super helpful. And that's because it allows you to just determine the order of your data. And so all you need to do is pass into it a numeric vector, and it will return to you the order. And this is in its position. Okay, so it defaults. Yeah, so by default, what it will do is it will do it in an increasing way, but you can control that with the decreasing argument. So you can turn decreasing equals to true. And when you put the order function, you'll get a set of numbers, and they correspond to indices corresponding to the order of the numeric. So we have 10, 20, and 30 here. And so we have it as decreasing equals true. So it will start with, this doesn't look right, actually. 20, 10, 30. Well, yeah. I'm not sure if I'm going crazy. Maybe I need to just drink some more water. Yeah, it is correct. I'm just struggling with my brain. Sorry. Yeah, because if we're going decreasing it goes 30, 20, 10. So 3, 2, 1. Yeah, I'm sorry. I was just being a bit slow in that moment. But yeah, so by default, it will be increasing, so it'll be the reverse order. Okay, but it just gives you the indexes. And this is really nice because then you can use that to reorder data frames or reorder vectors. So in this case, what we're going to do is reorder our 10, 20, 30. And so you do the order function on test order, so 10, 20, 30, and it will order them in the correct order, but you can also change it to decreasing equals true, and it'll flick it around. Order is one of those functions that has inherent capabilities to handle NAs. So if you remember, we talked a little bit about NAs this morning and how they're these placeholders where there's just no information there. And it's better than having no information there because R can use the factors in NA to know what to do with it. And so order has this parameter in it called na.last. And so by default, it's going to make the NA values all the way at the bottom of the order, so you don't really have to look at them. And so you can do that with na.last equals true. You can also turn it to false if you want, and they'll come to the front. Yeah, so we just have this NA in this test order. Cool. And so this is where we really use order is in these data frames, because quite often you want to be able to look at the top of the data frame and say, which of these are the ones I care about? And so in this case, we're looking at survival time. And so we want to know who is surviving the longest. And so you can take your data frame, you can say, I'm just going to look at survival time. So we can use our shortcut here with the $. And we're saying we want decreasing because we want to look at the biggest number first. And then we use this to index itself. So in this case, we're not subsetting the data at all. We're just reorganizing it. And so indexing doesn't have to be about subsetting. It can just all be about organization and ordering. And so here it nicely orders it. So I use this all the time. If you imagine, if you get some gene expression results, maybe you want to look at the gene that's expressed the most, or maybe you want to look at after you do log2 fold changes, you want to see the genes that change the most, or the ones with the most significant p-values. So order becomes very important for these data frames. And you can use order, like I was saying, to just as an arranger. You're not trying to subset or anything. It's all about arranging. And you can arrange over multiple columns. So in this case, we're arranging over type first and then survival. Okay. And so if you remember in the factor, we said that male is first in this, I believe. No, it's decreasing. Okay, we said that female is first because that's the default. And so that means because we're going decreasing, the male is higher. And so we're organizing by type. So male will be first, then female. But then we're also organizing by survival. So it'll also, between the males, it will show us the ones that survive the longest first. And then likewise with the female. So this means you can have this kind of hierarchical ordering. So you can see multiple classes to order by. So this is nice. So a common other thing to do with data frames is to try and join them together. Okay, we have a question. To do that, would you have to set up the factor with order? So if we remember with factors, by default, it will go alphabetically. So it will always have an order. It's just, is that order important? Okay, is there anything you want to actually look at first? And if that's so, that when you set up the factor, you can control the levels to the order that you want it to be. But if you don't care too much which one's first, then you can it will just do it alphabetically. Okay, so joining data together. So in this case, we have two data sets. we have basically two forms of metadata. We have these patients. We know that the gender of some of them, we have their survival time, but then in a separate piece of metadata, someone has collected height information, but only from some of the patients, okay? And this, anyone who's doing any clinical studies, this is something you probably recognize and probably regularly have to deal with. And so to deal with this, we use a function called merge, okay? So merge will take the data frame 1, data frame 2, and it will find the column in common, or you can specify the column in common, and it uses that as a index by which to merge the two together. And so in this case, we are saying by equals 1. So that means the first column is the index, essentially, the key by which we're going to merge these together. Okay, so it will look for where patient 1 and patient 1 exist, and then it will add the extra information. And then we're saying all equals false, okay? If you say all equals true, it means patient 4 will also be included, but there'll be an NA for height because there's no patient 4 in the height. All equals false means it will only include the data sets for which you have a the full information. Yeah. You can also control this in greater detail by saying by.x, by.y. So you can control, say, if in this one, the key is in the first column, but in the second one, the key is in the second column, things like that. But merge is a super useful function. And once you start to get to play with it, you can use the question mark merge to get more information about how to control it to even more finer detail. Okay, so we're going to do a quick poll on data frames. Okay, I'll give you a minute to do this. We have 10 more seconds for anyone else participating. Okay, let's share the results. Okay, so we had a couple of you say you can use the $ to access rows. Okay, so the $ is a useful data frame specific feature, but it only works with columns. Okay, so the special thing about data frames is it's each column contains specific information that is all the same data type. And so there's a lot of operations which focus on just columns. Okay, and the $ is one of them. When you do a cross with rows, it's a mixture of data types and it's a bit more complicated. And so there's less functions and capabilities to work with just the rows, because normally you aren't working rowwards, you're normally working columnwards. And so the $ cannot be used to get at the rows. Yeah, they can contain numeric and characters as long as they're in different rows. The merge function is used to bring two data frames together. Yeah, we just saw that. And the $ can be used to create columns. So a lot of you missed that bit. Yes, you can just use you have your data frame. I can go back to that real quick. I think it is here. No, did I go past it? I went past it. Here it is. So here we're creating a new column. This column doesn't exist up here. We just put the name in and then we assign in the data that we want to assign in. Okay. So $sign is super useful. It doesn't add any extra functionality really, but it just means you can be better. You can do things quicker and easier. So we had a question from Adam. Is there a way to save the console outputs? I want to save my R script and console together. Yes. The answer to the question, which you answered yourself, is R Markdown. R Markdown is fantastic because you can control exactly what inputs you have and what outputs you have, and it will all print it all together. You can also include what computer you ran it on, things like that. And so it creates this nice reproducible report, which is a perfect snapshot of all the code you ran and all of the output responses and the machine and everything you ran it on. So you answered your own question. We will get to using R Markdown, and it will hopefully be just what you need for when you actually get to doing R coding with your own analysis. Okay. Okay. If you need to import a big table to create a data frame in which most string columns are factors, it can, yeah. So it depends. So yeah, Jean, I don't know, Jean-Nicolas, I don't know why I'm trying to do an accident. If you're importing a large table, it can make it easier, I guess, if you want to put strings as factors equals true, so that you can actually speed things up. Because then you wouldn't have to specify that each one of them is a factor. That said, as I mentioned before, converting from a character back out to a from a factor back to a character isn't the easiest thing to do. Quite often it gets upset, and it won't drop the fact that it has the factor properties, and so it will just stay a factor, even though you're telling it to be a character. But there are, depending on how you build this, right? If you're putting together several vectors that you already have, it is quite straightforward to just wrap those in factor, right? Because they already exist, you've created them, and as you create them, you just tell them they're a factor. When we get to tidyverse, there is a ways to import data frames from outside of R, where you directly say, I want this row to be an integer, I want this row to be a factor, or this column even. This column's an integer, this column's a factor. And you do that when you import it. So that's probably the easiest level of control, because most of the time you are not just creating data yourself in R in a session by writing in vectors. Most of the time you're importing it from like a CSV or an Excel file or something like that. And then you can have that control when you're using the tidyverse and tidy packages for importing. And so when we go over that on Wednesday morning, that will hopefully augment some of the stuff that we're going over now and just give you a little bit extra capabilities. Okay. So just looking at the time, I think we're going to be running a little late, but hopefully not too late. Okay. Yeah, because we have about 30 more slides to do in 10 minutes. So, but I will endeavor to get through it without wasting too much time. Okay, so lists are the final data type we'll look at. So we are nearly there for the data types. And so lists are really, lists I find were the hardest to get my head around when I started to learn to code. And that's because they do everything. They're kind of a jack of all trades, but the master of none kind. And that's because they are like a general container that you can put anything in. Okay, so they're not optimized necessarily to work in very specific ways like data frames or matrices, but they're optimized to just contain data. And I think that'll become clear as we go through this. So it doesn't matter what the data is. It doesn't matter if it's unequal lengths. It doesn't matter if the dimensions are different. It will contain it. And so in this case, we have 3 elements. One of them is a numeric vector, length of 4. The second is a matrix. It's a 2x5 matrix. And the last one is a data frame. Okay. So these are 3 very different data types, different properties. You'd have a hard time mixing them together. And what we can do, though, is we can just say list. We surround it all in the list function. We have commas separating each of the elements. And it doesn't complain. It takes it. And then when you write in my list to see what's contained in my list, you can see it has 3 entries, 1, 2, 3, and you have your 3 objects. So it's kind of just this box that you can put anything in, and it has these different slots, and anything can go in the slots, and they'll be contained together. And so just as with vectors, matrices, data frames, you can add names. And so you can do that in a very similar way to what we did with the data frame. So when you did list, you can actually specify the name when you're creating it by saying, here we have first equals first element, second equals second element. Okay, and now each of these 3 different slots will have the names. Okay. Indexing with lists works in a slightly different way, though. We still use the square brackets, but to get out the elements in your list, you have to use 2 of the square brackets as a double square bracket if you actually want to retrieve it. And so if you use a single one, okay, so say we want to get the first element back. If you use a single bracket, what it returns is another list that has just 1 element. Okay, so it doesn't return the object, it returns a list, a single item list containing your object still, but it doesn't get the object out. But if you use the double square brackets, it actually goes into the list, grabs it, and then returns it back to the top level. Similarly, you can also use the $, again, with list, and as long as it's named, it will return the object directly, okay? So I hope that makes sense. There's a clear, like, different way in which we index, and that if we just use a single square brackets, it returns the object, but it's still wrapped in a list. Okay, and so if we really want to get it back out, we have to use the double square brackets. One of the things that's also similar to a vector is you can use the C function. Okay, and this can combine lists together. So in this case, we have created our list of first, second, third. And then we're going to add a 4th. Okay. And so as long as this is also a list, okay, so you can see I'm converting it to a list here. I have 4th equals this numeric vector. So I'm making a numeric vector. I'm saying that this is a list. It's a named list called 4th for this entry. And then I'm using C to combine it with this list that I created up here. So C can just stick 2 lists together. And then when I index this out, I'm going to look at just the first and 4th value, because it would be too big for me to see on the screen otherwise. You can see that the first and 4th value are the first value from this and this value I just added. So you can see lists have this kind of weird mixture of features, so this is very vector-like, but in the previous thing, we were able to use data frame-like nomenclature. to grab stuff. So it inherits different properties from different other data types. And so you will notice I made it clear that we were joining two lists together, right? If I didn't put this function here and I was just connecting a vector to a list, what happens is it will consider each position in a vector to be its own unique part of the list. So you can see we have, I'm only extracting 3 through 5 after doing this. We can see we have the entry from, that's our data frame that was in the list. And then the 4 object, the individual elements in the vector are separate entities within the list. So yeah, so there's some nuance to working with lists, but they can be really useful because you can then just put lots of things in there together, and then you just have one object that contains all your information that you need. You could then save this and then pick it up later, and all your information will be in one object altogether. Sometimes though, what you want to do, because this is quite a complicated structure, it's not what we consider flat. So flat would be something that's like a one-dimensional vector, okay? So to flatten the list, what you have to do is use a function called unlist. And what that does is it will take everything out. So here we have our example here. This is our list. We have first slot is first, second slot is second. We have numbers in each. They're all numeric vectors. And we unlist, and then it just becomes a vector. Okay, and you can see that the first slot is here, the second slot is here, and there's no more any hierarchy in the list separating them. There's no difference between slot 1 and slot 2. It's all just one character or one numeric vector. This can be useful though if there is if you have a list and it's made up of things that are consistent in size and you were actually aiming to turn it into a matrix. So say each of these data points is each of these slots represents an observation, and you have 3 data points in each observation. You might want to turn that into a matrix because it's easier to work with. So you can take your list, you can unlist it to turn it into a vector like this. And then you could use that as your input for a matrix. And so then when you do this, you'll want the number of rows that are equal to the length of your list. And and then you can have some names from the names of your list as well. And so we're basically turning this list into a much more usable object in this point. Okay. So we're going to go over coercing data classes. So we've talked a little bit about coercion with regards to factors. If you ever want to know what class your data object is, you can use the function class. It will tell you. So we have our matrix from earlier on. It's a named matrix. We can ask what class it is, and it'll tell us it's a matrix or an array. Similar with our data frame example, we get back data frame. And so we can use these as dot functions to convert between. And so, for example, here we have our named matrix. We can turn it into a character, and we get back a character vector. We can turn it into a vector, and it's just a vector in itself. It's still numeric, but it's a vector. We can turn it to a data frame or to a list. Okay. And so these as dot functions allow you to quickly interchange between data types. Okay. as I mentioned before, factors can throw errors when you do this or be annoying. And so that's the one exception for this, I'd say, quick and easy interchange, is factors can sometimes get upset when you do this. Okay, I'm going to throw up the last poll, which was about lists, to make sure everyone understands lists. And then I'm just going to quickly double check what we have left. Okay, so the last section we're just going to do about import and export data. Okay, it's fairly straightforward, so we'll get through it pretty quickly. Okay, I'm going to give you 20 more seconds, and then we'll see how everyone's done. Okay. Right, so I think most of you got this. You can combine lists with the C, right? So it's vector-like in that nature, but you can also use the $ to access elements of a named list. So it's like a data frame. A couple of people fell up on this trap. It's the square brackets that you use the doubles for, okay? So if we remember, parentheses are for functions, square brackets are indexing, double square brackets are indexing of lists. Okay, and then no one said lists can only contain certain data types, because they seem to be able to contain everything. Right. So the last thing we're going to cover before the break is taking data from external sources and exporting data once you've done some manipulation of it. Okay, so most of the time, you're not going to be just making this yourself in R. You're going to be actually reading it in, often a CSV, Excel file, things like that. And so you'll often get a file that looks like this. Okay. And so there's very easy ways to manage this. There's functions that are inbuilt into R. One of these is read.table. Okay. And so this is a read.table function. And so this path should work for you if you have the right working directory. In the data folder is a CSV called read this table. Okay. And so when you do read.table, you point to this. You can then tell it a couple of other parameters. It has a separator, which is a comma. So a CSV file is a comma separated file. So that means in between each data point in the actual in the file, there is a comma, and that says this is the end of my column. And then header equals true. So this means is the column names, essentially. Okay. So you can read this in, you can give it this extra information, and you'll get a table. Nice and easy. So we're just looking at the first 4 rows and the first 3 columns. Okay. So some of the most common data types you'll see is CSV. That's the one I use most of the time. Another one you might see is a TSV. That's a tab separated. And so you can encode the separator using this. That means tab. Okay, and we talked about the header. That just means the columns have headers or column names. And so you can just turn it on and off depending. Read.table has a ton of options. There's a ton of different kinds of data frames you can read in. You can just look at them with the question mark. You can also specify, oh, someone's writing about table. Okay, I think that was a copy and paste mistake. So you can also use the row names argument to specify a column that you want to use as row names. Okay, so in this case, the gene name information isn't actually super useful. It might be more useful to have that as your row names. So you can say, hey, I actually want row names to be column 1. Okay, and so you do exactly the same, and now it's read in as row names, and it's not read into the main data frame. And so whenever you read anything with read.table, it's assuming you're getting a data frame. It's assuming there's different data classes, and it can handle both of them. Similarly, like as we talked before, if you want an old version of R.3.5, R3.6, for example, the strings as factors will be set to true. So you might want to set it to strings as factors equals false, depends what you're reading in. But for most of us now who have newer versions of R, this is less of an issue because it's set to strings as factors equals false by default. And yeah, these are some other things to keep an eye out for. These are other arguments you can add for read.table. One of them is skip. Say you want to skip some lines. Quite often you'll find that, say you get qPCR results back from a machine or something like that, it will have just a bunch of junk at the top that you don't actually care about, and you want the numbers at the bottom. And so you can skip those lines. Or you can, if you want to only read in lines that have a specific variable on them, or the lines start with a specific thing, you can use comment.car. And so this can be used to skip specific lines. Okay, read.table can also work from a web address. So we often have CSV files online, right? And so there's a CSV file here that you can read in directly from the internet. And you can also read in stuff from Excel or from the clipboard, which maybe you copied from Excel or something like that. And so this isn't the code to be able to do that. Okay, so it has a lot of flexibility. But sometimes you want to read something in and it's massive, like really, really big. And so there's another function called scan, which allows you to read things in, but you have a tighter control over what you're reading in. But it doesn't make it into, it isn't as a nice a format once it comes out. But here it basically creates this big vector. But here you're saying, I'm going to read in this data table, use the separator again, the comma. I'm going to say what it is. It's characters, and I'm going to skip the first row. Okay, so in this case, that's actually one of the arguments for read.table as well, I believe, is what. So you can actually confer if you want something to be a factor or you want it to not be a factor, and you control versus the columns. So that gets to the question that John Nicholas had. Okay. And so much like you can do read.table to get data in, you can do write.table to put it out again. And so once you have a table, you do write.table function, you say what table you want to write out, and then you say where you want to write it. And then you can put in a separator. So in this case, we're creating a comma separated data object or file. Yeah, we're creating a CSV file. So we want to have the separator to be a comma. And again, you can control arguments. So if do you want the row names to be carried forward into this? Do you want the call names to be carried forward into this? Again, there's lots of parameters to control the input and output. a couple of very useful functions are head and tail. This allows you to quickly see what's in your data frame. So we have this object called data. And so I use head all the time. And it's really important to just know what your data looks like as you keep changing it and looking at it, modifying it and such. And so if you use the function head, it will show you the first 6 lines, or tail will show you the bottom 6 lines. So you can check what the data frame looks like. You can make sure it has all the columns you're expecting and things like that. So here's tail. You can also control how many rows it shows by just doing a comma and then a number, however many you want. Okay, so the last thing we're going to cover, and it won't take very long, is Rio. Rio is our input-output package. And so most of the files we're talking about, like CSVs, TSVs, these are very files that are used by us who are specialists in this. But most of the time, you're going to be working with people, or you are one of these people who's predominantly using Excel, right? Or SPSS, or things like that, MATLAB. And the base packages in R don't cover input and output of these things. So there's packages like Rio, which can help increase that capability. And so when you want to use Rio, just like any other package, you first have to install it. Okay, and so to do that, you use the function install.packages, and then you'll put the name of the package you want to install. So in this case, you're installing Rio. If you followed the guidelines for the course, you would have installed all the package ahead of time because it can take a little while to download. Depending on the package, it can take 5 minutes to install, or it can take 5 seconds. Once it's installed, it means you have it on your computer. It doesn't mean it's in your environment. So to get it in your environment, so it's easy to, so you can actually start to use the functions, you have to use the library function. So what you do is you write library, or in this case, chuck Rio inside. And that means all of the functions within Rio are then able for you to be used. And so Rio has a very simple function called import. And what import does is it recognizes what the extension is, and it reads it in the most appropriate way based on that extension. So it doesn't need as much information from you to tell it what it is, because it uses the file name. So in this case, it's reading in the CSV, no problem. But it also does this for Excel. So you can do .xls, and it will read it in. And so in this case, this Excel document has multiple sheets. And so you can actually say, which sheet do I want to read in? So I say which equals 2, so it'll read in the second sheet, or it'll read in the sheet called metadata in this second option. By default, you'll only get the first sheet, okay? But you can control which one. You can also use the function import list. And what it will do is it will create a list, and in each slot in the list will be the sheet, essentially. So sheet 1 will go into slot 1, sheet 2 will go into slot 2. And so you can see that here. This list, the table is actually a list now. And if you look at the names, this corresponds to the names of the sheets from this Excel document you just read in. And so we can use the standard accessors to grab them. So we can look at the $sign or the double square brackets to look inside. So we're using the $sign here, and we're just going to look at the first 2 rows. And you can see we have a bunch of gene information here. And then we use the $sign for metadata, and we get a bunch of metadata for the experiment here. Okay. And then as easily as you can import, you can then export. Okay, so you just use export, and it infers from the extension what kind of file you want. Okay, so again, you don't really have to specify much. It will understand the fact that you want an Excel document by the fact that you've written out that you want an Excel document in the file name. And so again, the first argument is the thing you want to export. So in this case, we're just exporting the first page of this sheet. And you can also export lists as well. So you don't have to do anything particularly complicated. If you have a list like we do have a table, right? As long as it's a named list, you can then export it. Okay, and what it will do is it will just do the reverse of what we did for import list, and it will export each of the elements to a list into a separate sheet in the Excel document. Okay, so that is Rio, and that is us for now. Sorry we overran by nigh on 20 minutes. Yeah, Rio is super useful for working with these standard formats that people work with, but aren't as, are a little bit more complicated than when people first came up with R in the first place and the base packages in R. If anyone has any questions, I will be here. More than happy to answer questions. And if anyone wants to dive into the exercises, I can help them. We're going to have a little break. We'll be back at 3. So we've got a 40-minute break. And then we're going to get into the real nitty-gritty of using loops and things like that. And this is where I guess the power of R will really come to the front. And you can start to see how you can create your own functions and use them to iterate over your big data objects to do something for you that was going to save you a ton of time. Okay. Well, I'm going to turn off my screen and my mic for now, and I will see you all in a short period of time.